and now we will going to begin our fourth session of the day, and the chairman of the session is Professor Divakar Rakshit, and the reporter for the session is Dr. Abhishek Gautam. And let me introduce to the chairman of the session. Professor Divakar Rakshit is an associate professor at IIT Delhi with 19 years of experience in thermofluids, especially optimization of energy systems. He has a PhD from University of Western Australia and postdoctoral research experience at CSIRO Australia. His special interest lies in energy storage devices, thermal fluid studies of solar energy, coupled heat exchanger designs, energy conservation buildings, green building concept, water heat recovery, transient modeling and simulation, multi-phase flow studies, and he has expertise in the design of HVAC systems and formulation of standard for indoor environmental quality, preventing infectious diseases transmission in enclosed spaces. His research has been sponsored by DST, Ministry of Education, Government of India. Besides these, Professor has got funding from IIT Delhi for developing a thermal devices characterization laboratory. He has a track record of publishing 70 research papers in different reputed journals, 14 monographs, and around 50 referred conference papers. And the reporter of the session, Dr. Abhishek Gautam, has completed his PhD from Department of Hydro and Renewable Energy, IIT Roorkee, under the supervision of Professor R.P. Saini, and in the field of solar thermal energy storage. He is currently working as an institute postdoctoral fellow in Department of Mechanical Engineering, IIT Bombay, India. He also has 3 years of experience serving as assistant professor and lecturer in various Indian engineering institutions. His research area extends to solar thermal energy systems, solar thermal energy storage, heat transfer enhancement techniques and heat exchangers, and non-conventional thermal distillation method. There are 11 research papers published by him in different international reputed journals. And with this, now the session is handed over to the chairman of the session.
Thank you, madam, for the introduction. So once again, I welcome you all to this fourth session of the workshop. So I think without any delay, we can invite our speaker. So Professor Zhenjun Ma, who is from University of Wollongong, Australia, and basically he works in Sustainable Buildings Research Center. So I request Professor Ma to unmute himself, and over to him for my presentation. Thank you.
Thank you very much for the chairman. So good afternoon, colleagues. So I will introduce the work we did over the last 10 years on the solar photovoltaic thermal systems and the integration of thermal energy storage using phase change materials with solar photovoltaic thermal systems. So I'm from the University of Wollongong, Australia. So some of you may haven't heard our university. So we are in the New South Wales, is very close to the Sydney is the international airport. Is only 1 hour drive from the international airport to our campus in Wollongong. So our university is a relatively young university. It only have 70 years history. So we are at the moment in the top 1% of the university in the world, and we are in the rank or in the QS ranking is 193 for this year. And for our research center is Sustainable Buildings Research Center. We are focused on the research, collaborate, and link with the industry to make our buildings more sustainable and cost effective. So over the last 10 years, we have developed a number of buildings and our living laboratories to demonstrate how solar energy technologies and thermal energy storage technologies can enhance the performance of our buildings. And we also developed a microgrid based platform to look at the integration of different renewable energy technologies and different energy consumers to the microgrid system to test the stability and the performance of different technologies. That's our primary focus. So in this presentation, so firstly, so I will give some very background information of why we are focusing in this area. And secondly, so I will give an introduction of the work we did on the solar photovoltaic thermal collectors and phase change materials, as well as the integration of both technologies with other building energy technologies. So the focus is really from the space cooling will have a great increase in the next several decades. And the prediction shown the world power consumption for the air conditioning will be increased by 33 times by the 2100. So that is a large increase based on the current level. And but unfortunately, and the technology used in these days is still based on the very old vapor compression cycles. So that's what invented around 100 years ago. So our primary interest is to look at renewable heating and cooling to replace or an additional solution for the vapor compression cycles. And we were thinking of the combination of renewable energy technologies and phase change material storage and effective solution to improve the performance and increase the efficiency. So and we all know, for the renewables, it's mainly for the solar energy is intermittent, and we have unstable of supply. It really depends on the solar radiation, and we don't have any supply in the night time. But phase change material, on the other hand, and higher energy storage density, and we have different materials available and different melting temperatures. So we were thinking that will be a very nice marriage between the two different technologies. So that's why we are interested in this area. For the solar photovoltaic thermal collectors, our interest is on the air-based, not a liquid-based photovoltaic thermal system. So the major reason is that if you have been traveled to Australia, so you will see a lot of roofs and this kind of roof structure. So that is a steel product, made of steel product, the color bond product. And this kind of roof have a certain of valleys, and they are very easy to build. So that our focus is look at whether we can use this existing roof structure to increase the performance of the buildings by using this current roofing structure to make it a photovoltaic thermal collectors. Just place solar panels on the top, then using these valleys and the air channel to form the photovoltaic thermal collectors. So as shown in this image, so you have PV modules on the top, and we can use these valleys and air channels. So this is very easy to make. And the merit of this technology is that in the daytime, so we have a very strong solar radiation, so we can generate electricity. At the same time, we can generate high temperature thermal energy. So this amount of thermal energy can be used for the different purpose. can be used for the space heating inverter, can also be used to drive other heating or cooling technologies in the summer case. In the summer, we require the cooling, so they can drive other air conditioning units for space cooling. And also in the nighttime, we can use sky radiative cooling to pre-cooling the building and then reduce the energy consumption in the next day. So that's our interest is really in the air-based photovoltaic thermal collectors. So we start from this concept, and firstly we build a model to understand the performance variations. So for instance, we build a resistance capacitance model to understand the major influence of different parameters and what will be the behavior of such technology. And for this model, and we validated using the data from our building. So we presented in our building, we have a photovoltaic thermal system installed on the roof, and also in this residential building, we also have a photovoltaic thermal system in this area. So this is the photovoltaic thermal technology. So this is just the solar panels. And in the behind, we have a land plate solar collector for domestic photovoltaic. And so you can see that from the model validation that we get reasonably good data for the measured and modeled data for the outlet air temperature from the solar photovoltaic thermal collectors and also from the power generation. So both sets of data, they matched quite well. And so we also, based on this understanding, we further extended our design is to increase the outlet air temperature of the photovoltaic thermal collectors. The reason is we want to use this high temperature air to drive the air conditioning in the summer case. Otherwise, so this air will be exhausted to the ambient air and it's not really used. And we looked at different solutions. One is a combination of photovoltaic thermal system. So this side, we have a photovoltaic thermal system. And this side, we don't have a solar panel on the top. So that is from the solar air heater, just have a heat up the air. So by doing this way, so we have electricity generation in this side, and you can further increase the temperature of the air from the outside, from the outlet air. And that is one option we investigated. And another one is we looked at using the heat pipe to also increase the outlet temperature of these technologies. And I will show you in a later case and why we want to increase the temperature and use this temperature to drive other technologies. And we also developed a solar plankton-based benchtop test rig, and then that's integrated with a photovoltaic thermal system and phase change material storage. So this test rig can change the orientation, can change the slope, and can change the air flow rate inside of the ducting system. And in this test rig, so we placed over 50 thermocouples in different locations to understand performance variation. So for instance, at the inlet, so we have this group of thermocouples to measure the surface temperature of the bottom surface temperature of the solar panel. We measure the air temperature inside of the channel, and we also measure the bottom temperature of the PVT system. And in the middle, and we installed the same number of thermocouples and the outlet, and we also installed the thermocouples. And we also measured, you can see that the weather station to measure the wind speed, the wind velocity, and relative humidity and solar radiation. And in this test rig, so let's see the outlet air from this side. We directed into this photovoltaic. That's the patient material storage, and inside this box we have this kind of material, is a brick material. So inside is like the brick, but inside is the patient material. So we investigated the melting process of such kind of material using the hot air from the outlet of the PVT system. We also installed a number of thermocouples to investigate the temperature variation and the profile inside of the PCM thermal storage. And based on this design test rig, and we also investigated what will be the likely phase change material that can work with building integrated photovoltaic thermal collectors. So we worked with the Fraunhofer Institute for Solar Energy System in Germany, and they have a strong team on the phase change material. So we investigated for this kind of materials that may be likely be able to work with a PVT system and suitable for the different applications. So based on the different melting temperatures and based on different enthalpy of the heat of fusion. So that can be used with BI PVT, building integrated photovoltaic thermal systems. And then we did a lot of experiments based on this test rig. So we investigated, so that's the basic information, used the material, PCM materials used in this test rig and the PV panels used in the test rig. So for the phase change material, so we used S21 is an inorganic material, and we used a brick number is 12 bricks. So this kind of bricks, we use 12 in total. And so this material is a melting temperature is 22 degrees centigrade. So that's its density and latent heat. And so based on these materials, so we investigated the different air flow rate. So for instance, so we changed the air flow rate, increased air flow rate based on the same slope of the panel and based on the same orientation of the PVT system. And then we also varied the slope of the PVT system. So we increase the slope of the PVT system, but under the same air flow rate and the same orientation. And the last group of tests, we vary the orientation to look at the solar radiation on the surface, but under the same air flow rate and the slope. So we investigated the efficiencies of electrical generation and the thermal efficiency of the PVT system and the thermal efficiency of the PCM thermal energy storage. And these are some test results. And so this one, the first group is the variation of the air flow rate. And we can see that this is the electrical efficiency is nearly constant. So vary the air flow rate didn't really cannot really make great change in the electrical efficiency. But then we look at the thermal efficiency of the PVT system with the increase of the air flow rate. The thermal efficiency of the PVT system is greatly increased. But thermal efficiency of the PCM thermal energy storage is greatly decreased because you have a slow air flow rate. So you have a large temperature difference between the inlet and the outlet. So you have a large temperature inlet, and in this case, you have a large flow rate. You have a smaller temperature inlet compared to the first scenario. So therefore, the overall efficiency is same, is decrease with the increase of the airflow rate. And ideally, it really depends on, your interest is on the efficiency of the PVT system or efficiency of the thermal energy storage. And the second group is for the slope change, the variation of the slope of the PVT system. So you can see that with the increase of the slope of the PVT system, electrical efficiency is still very similar, but the thermal efficiency of the PVT system is usually in the 25. That's nearly the optimal slope in this climate condition. And thermal efficiency is very similar. It's really for influence the thermal efficiency of the PVT system. So 25 degree is nearly the optimal degree in our climate. And then for the variation of the orientation, so 90 is 0 in the north side, usually is best orientation in this climate will have lots of solar radiation on the surface. So you can see the electrical efficiency is pretty high compared to the other two, and similar to the thermal efficiency of the PVT system, but you have a decreased efficiency of the thermal energy storage. The overall and the efficiency is very similar. It depends on whether it's your interest is on the electrical efficiency or thermal efficiency. And we also, based on the data we measured, we look at what is the optimal airflow rate on the different conditions. So on the different outdoor air temperature and on the different solar radiation and the sky temperature, and as well as the status of the thermal energy storage. If the thermal energy storage is fully charged or partially charged, the optimal flow rate is really will be different. So we found that the optimal flow rate is a function of all these parameters. Function of the solar radiation, ambient air temperature, and the sky temperature, wind velocity, and the status of the PCM thermal energy storage. So this means that under the real charging process and discharging process, we need to continuously to determine the optimal flow rate in order to achieve the best performance. And based on the GVT, solar photovoltaic thermal system, we also investigated transpired solar collectors. So different from the solar photovoltaic thermal system. So this technology didn't generate electricity, but it mainly generates thermal heat. And so this is the transpired solar collector we installed in our building for winter space heating. So the design of this technology is very, very critical. And we need to, so this is the facade, we need to make sure in the summer conditions, we don't have strong solar radiation on this surface. But in the winter conditions, we need to make sure we have we have a maximal solar radiation in this surface, so that we can provide heating for indoor space condition. And so the design of this technology is really depends on the design of the building. So you can see a lot of, maybe you couldn't say very clear, lots of small holes on this facade. And shown in this figure is a lot of small holes on this facade. So we usually have a fan on the top. When the fan is in operation, it will suck the air passing through these small holes. So then you have, because of your solar radiation, it heat up the air in the channel. The air temperature will be increased. And in the top this area, it can may reach 50 degrees centigrade. Then you can direct this air into the space for space heating. So that's another technology. So this technology cannot really be used in the summer daytime, but in the nighttime you can also use the nighttime sky radiative cooling to a condition of pre-cooling the building. So we did a lot of measurements in our building. So we installed different thermocouples to measure the temperature and the different locations, different height, and different for the surface temperature or temperature of the air in the channel. And we also measure the air flow rate and to determine the best performance. So for instance, so that is our measurement setup. So we have so these dot points, they are temperature sensors. And so this is the outlet air temperature, and we direct the air in this ducting system. So we measure the flow rate and or air velocity in the air ducting system, and with the fan in operation and suck the air. Then it goes to, so we will measure with the temperature distribution inside of this technology. And so these are some measurement data we example of the data we measured in the past. And so this curve is the air flow rate in the ducting system. And so these different curves, so the top of these curves is the temperature of the air and different locations inside of the ducting. And so basically, so this technology can increase the temperature. For instance, in the winter case, from 20 to 50 degrees centigrade. So this will be very, very valuable for the space heating in the winter time. You can reduce a lot of electrical demand. So that's another solar collectors we investigated. So based on these solar collectors, so we also developed and tested the performance of shell and tube phase change material thermal energy storage. So the idea is our interest is on the centralized thermal storage. And we think that is because we can control the melting range and the charging rate and discharging rate of the thermal storage, rather than if you, in many scenarios, they put this material on the facade, on the building envelope. So in that case, you cannot really control whether materials can be fully charged or fully discharged. So therefore, we try to make this material more useful and can fully be functional. That we try to look at the centralized thermal storage. And so this is we tested a shell and tube phase change material storage. So our design is based on the modular design. So this is the single module, and if you have so this is inlet outlet section, and if you have want to increase the capacity of the thermal energy storage, so you have multiple units you can put all together and get the different capacities. So in this test, we investigate 3 different layouts of the tubes. One is a single serpentine. We have inlet and outlet from the inlet from this side and outlet from the other side. And we have a double serpentine, so inlet from this side and outlet from the same side. And we also investigated this configuration, spiral configuration. So we try to understand the performance difference and which one offer the best performance. And in this case, so we use that this material we use in sodium acetate trihydrate material is inorganic material, is very cheap. And so in this case, we use the 16.2 kilogram PCM. So that is so inside is a working fluid, and the PCM is filled in between these tubes, is outside of the tube. So so we have this number, the length of the tube we use in the experiments, and in this case, so the melting temperature of this material we use is 58.4 degrees centigrade. It's mainly for the domestic hot water applications. And this is a test rig we developed. And so in this test rig, so we have an air source heat pump, generate hot water supply to this hot water tank, and we have an air-cooled chiller, so which generates cold water and store it in another tank. And this is the water pumps to circulate the pump, to circulate the working fluid of the water, is really water in this case, for passing through the thermal storage unit. So in our experiments, we just tested two different layouts. One is a double serpentine and another is a spiral. So we didn't really test a single serpentine configuration. And so this is the air source heat pump connected with the hot water tank, then goes through in the charging process. So that this hot water will go through the both configurations, and so we monitor the temperature in the tank, and we monitor the flow rate and the temperature inlet and outlet of each system, and we also install the 3 thermocouples inside of the thermal storage. And so this one is used in a discharge condition, and cold water is passing through the PCM storage, then discharge the thermal storage. So we tested tested the performance on the different conditions. So one is so that's in the charging performance test. We did test on the different inlet water temperature of the thermal energy storage. One is 70 and the other is 75 degrees centigrade. And we also investigated the performance variation on the different water flow rate. 2 different water flow rates we investigated. So similarly, under the discharging test, we used the same flow rates and what we used in the charging test, but we used a different low temperature for discharging of the thermal storage. So this is some experimental results from the experiments. So the one is so you can see, so this is in the charging process. So this is inlet temperature into the both thermal storage, both with different configurations. You can see they are very, very similar. And this so the middle curves, so these curves are the outlet temperature or water temperature from the thermal storage. So these the bottom ones, they are the curves, they are the melting, the temperature of the phase change materials. And from this one, so that we investigated under the same inlet water temperature, but with different different flow rates of the working fluid. And you can see there's some small difference. So you can see there's small difference between the PCM temperature and outlet water temperature in this case. But if you increase the flow rate, you can see a large relatively large difference compared to this one between the two sets of temperatures. And the bottom two figures showing under the different flow rates, but we further increased the inlet water temperature. You can see if we increase the inlet water temperature, clearly the difference between these curves and these curves increased. So this means we will result a faster charging process. You can reduce the charging time. And similarly for this scenario. So then we also did a test under the discharging test, and for the both scenarios, so the inlet temperature is quite stable for different tests, and similarly under this temperature inlet temperature condition, so you can see there is the variation of the material. So you can see this very obvious variation. That's because of the supercooling of the inorganic material. So that's very clear. That's also a disadvantage of this kind of inorganic material. And similarly, so you have a low inlet temperature in the discharging test. You have a large difference between the temperature and of the outlet water temperature and PCM temperature. If you increase, so this temperature difference will be decreased. So based on these observations, so we did a sensitivity analysis to look at what are the major parameters influence the design of this thermal energy storage. So in our analysis, so we use the performance indicator of the total time required to charge the PCM thermal storage with a liquid fraction of the material. One is 90% and another is 95%. So which means in this case, 90% of the PCM in the thermal energy storage is changed from the solid phase to the liquid phase. And this one is 95%. And so that's either for the sensitivity index, and this is for the different parameters or different variables we investigated. And the large indicator means the large influence. So you can see this one has a very large influence on the performance of thermal storage. So this is X4 is the inlet water temperature. So this is very similar to our observations in the charging test and discharging test. And the second high the value is for the tube length, so the length of the tube inside of thermal storage. And the third one is the water flow rate, and other variables such as layout didn't really tell show a very big difference, and shown in the figure before, and the difference between the different configuration, either double serpentine and spiral configuration or layout, they didn't really show a big difference. So based on these investigations, so we also looked at the variation of the time of charge when change the variables of the major variables from the sensitivity analysis. One is the inlet water temperature and the turbulence and water flow rate and PCM thermal conductivity. So look at the variation of these variables. What will be the variation of the time of change? So in this case, so we use the make sure in the charging process, 90% of the PCM is changed from the solid phase to the liquid phase. So clearly, and so tube length shown the very different behavior compared to the other variables, and it seems at this point, so that's where we can nearly the optimal length, And if you can further increase the length, didn't really show a lot of benefits. But for the other parameters, they show the very similar behaviors. But in this simulation analysis, we considered for the 3 different scenarios for the single serpentine, double serpentine, and spiral. So you can see single serpentine show the worst performance, and the double serpentine and the spiral show the very similar performance in these 3 different configurations in these 4 different variables. They didn't show a great difference between the 2. So that is based on our understanding of the thermal energy storage design and our development of the GCN and thermal energy solar photovoltaic thermal collectors. Then we investigate the opportunities to integrate of this technology into building energy systems. So our focus is on the HVAC, the heating, ventilation, and air conditioning systems. So we did a lot of case studies, but here I show you 3 examples or 3 case studies what we did in the past. So one is we developed a new system. So this is a PVT collector, solar photovoltaic thermal collectors, and this is the PCM thermal energy storage. They integrate the heat pump. So this is the air handling unit. Either if you are working in the air conditioning space, so you know that is the air conditioning unit. And so in this system, so we have different operation scenarios. So for instance, so the PVT collector can generate heat and generate electricity, and the heat can be directly discharged to the ambient and or can be installed in the thermal energy storage and used later for space heating, and can also be directly used for the space heating or preheating. So different scenarios. So we developed a prototype for this HVAC system, and you can see so we installed this HVAC system in this building. So that's one of our given laboratories. So we installed in this building, and so this is our phase change material thermal energy storage we placed on the floor of the building, and so we use the same material, and we did in the experimental test is an inorganic material, melting temperature 22 degrees centigrade. And we also developed the control system to optimize the air flow rate, optimize operation, and the charging and discharging of the thermal energy storage. So I'm showing in this interface we developed for this building, and you can see that so they have different operational modes. So we can use natural ventilation, so we can use direct PVT for space heating, we can use the PCM discharging, and to make sure we can provide the same similar level of indoor thermal comfort, but with reduced energy consumption. And based on this system, we also developed a model predictive controller to optimize the performance of this system. And you can see so this will be integrated with the weather station and with the C-bus and the JC controller, and to control and optimize the operation of this system. So this actually our measurements. So this is a competition, solid cancelon, and in solid cancelon competition, I'm not sure whether you have noted the competition, and we participated in this competition. And that's our measured data during the competition. So this is our temperature measurements in the competition period, and this is the relative humidity measurement in the competition period. It's nearly in the, so these lines are the limit, so you need to control your relative humidity and the temperature in this range. And this is for the electricity generation of from the solar photovoltaic thermal system. And so this one is the consumption from the house, and this is net generation. So clearly we have much more generation compared to what we consumed in the competition period. And so this is the test result from the model predictive controller in the summer case. So we need to control the indoor temperature in this range. So clearly, so this is the real indoor temperature. It is in the temperature range. And in this case, so you can see, so in this, in the night time, we use the PVT for the pre-cooling using the sky radiative cooling, radiative temperature. And this is in the early morning, so we use the PCM discharge the cooling to condition the space to reduce the electricity consumption. And based on also for this system, so we investigated what kind of energy flexibility can be offered for demand response and demand side management. So we investigated opportunities using the solar photovoltaic thermal system and phase change material system to increase the flexibility of the building. So if you haven't know what is the energy flexibility, so energy flexibility is the ability of a building to manage its demand and the generation according to the local climate conditions and the demand from the occupants and the energy network requirement. So we have been, we were considering in the buildings there are diverse of flexible energy resources available. So from the energy generation perspective, we have solar panels, we can have wind energy, wind turbines to generate energy. So we have thermal storage, we can have electrical storage. And from the consumption perspective, so we have traditional energy consumption, we can have electrical vehicle. So we can manage this kind of energy system. And from the user side, so we also have change of occupancy behavior. From buildings, we have building thermal mass or rotation. So all these factors will provide different level of energy flexibility. So we investigated different scenarios on the different demand side management strategies. So I will not go through the details. So you can see, and in the first, this group of tests, we have PVT collectors. We also have phase change material storage systems. And in this second group, so we don't use PVT, but we use the PCM storage. And the third group, we have the PVT collector, but we don't use PCM storage. And in the last group of tests, we don't use any of them, just use a traditional air conditioning system with different demand side management strategies. So this demand side management strategy is really, if you have extra generation from the solar panels, you can either charge the PCM thermal storage or preconditional space using the additional extra energy generation. So we did this kind of analysis using the transit simulation. So that's the simulation system we developed. And we did analysis on the different electrical price. For instance, in the peak period and off-peak period, you have different electrical prices. And you have, so sometimes, for the different electrical, different profile for the electricity prices. So for instance, in this case, from the 4 p.m. to the 8 p.m., so you are the peak demand period, you have a high electricity price, and then the rest are the off-peak demand period. And this one is a little bit more complicated, and this is even more complicated. But overall, under the different, usually under the peak demand periods, you have a higher electricity price, and on the off-peak period, you have a low electricity price. At the same time, and if you have export generation, you can sell to the grid. So this is for the different scenarios we tested. You can see so this one is a thermal contribution. So that's from heat pumps. And for the blue ones, the thermal contribution from the GCM thermal energy storage. And the red ones are the contribution from the photovoltaic thermal collectors. And in these scenarios, we used both GCM and photovoltaic thermal collectors. And in this case, we only used GCM, but didn't use photovoltaic thermal collector. And this one we didn't use GCM. So you can see the variation on the different electricity prices for these different combinations. So they show the thermal contribution. And then we use the TOPSIS-based performance evaluation. So TOPSIS is a technique for order of preference of similarity to ideal solutions. So ideally, you can see the best scenario is in this range. So in this range. So this range, they either using both PVT and GCM thermal storage, or these scenarios, they only use thermal energy storage. So which means that using the thermal energy storage provide a much increased energy flexibility of the building. So second case study is another thermal energy storage we developed for another given laboratory. So this given laboratory, we actually participated in the solar decathlon competition in Dubai in 2018. So that's in the very high temperature humidity conditions. So we designed the HVAC system to integrate the thermal energy storage. So in this case, we used the water-based thermal energy storage to provide heating and cooling to the building. And so these are the thermal energy storage system we developed. Two of them, each one had 50 kilowatt capacity, and they linked with the heat pump to charge and discharge for conditioned space. And so this is how this thermal energy storage and HVAC system were installed in the building. And we also have that is inside, or how they were distributed inside of the building for the heating and cooling was delivered. And that's the inside, the configuration inside of the building. You can see, and that's the solar panels or radiant panels we installed in the building. And this is the installation of the HVAC system in the building. So you can see that thermal energy storage is in the east side of the building. So in this building, and we designed this thermal energy storage. So that's thermal energy storage system we developed. We used the S10 is a melting temperature around 10 degrees centigrade. Is also a inorganic material. So GCM is in the tube, and the water flow from outside for the discharging and charging process. And we also developed finite element model to look at the performance. And we also investigated which variables will greatly influence the design of this kind of configuration. So clearly, the diameter of the GCM tube will be the key variable. And so similarly, we also the control of the thermal storage is very, very critical to make sure it is fully functional. So we also developed a model predictive control to optimize the operation, and that's some metadata and So this is our simulation data, and this is the measured data from the real system. So overall, they matched very well. And so this is the measured temperatures in the different rooms of the house. You can see they are relatively stable with some large variations in the nighttime. So for the that's in the living space, bedroom, and kitchen area. So this figure shows the relative humidity inside of the building, and it also is very stable in the working time. So this is working time. They are they're relatively stable. And the last example I want to introduce is the PVT and PCM enhanced desiccant cooling system. So the idea is and PVT is only generate heating, and so this heat can be used for winter heating, but in the daytime, but in the summer cooling conditions, it cannot be really used. So we want to use this heat in the summer condition for provide cooling to the building. So that's why we look at the PVT and the solar air heater is really to increase the outlet air temperature of the PVT. So this temperature can drive the desiccant wheel. So desiccant wheel is really to achieve humidity control of the material of the ventilation air. So we have thermal energy storage is sitting here for the heat from the solar air PVT and the solar air heater can be directly used to regenerate the desiccant wheel, or can be used to charge the PCM storage and then use in the later for regeneration of desiccant wheel. So this is the electrical heater. If the heat or temperature is not enough, so we can use this device to provide sufficient heat. And so this is for some of you, if you know that from the desiccant wheel, so we have heat recovery, so we further reduce the temperature from the indirect evaporative cooler. So I really want to show you the value of using the PVT solar air heater and thermal energy storage to drive the desiccant cooling system. So this is our the configuration of the system. So this is really for the thermal energy storage. We used in the also in a brick, but in this case we use the paraffin length was considered and the PCM, and because the outlet air from the solar air heater is we prefer a little bit higher, so the material we use is varied between 55 and 75 degrees centigrade. And we did a lot of optimization, and so we use genetic algorithm-based optimization to determine the best configuration. And based on the configuration we determined, so we compared the value is the value of optimization in this kind of analysis. So this is the heating in the case study building with the heating demand and cooling demand. So in our case, so we have cooling in the January to the April and October to December. So we have a very small heating demand in the middle of the year. And in this case, we compared 3 different scenarios. One is the baseline case, the one baseline case 2, and the optimal case. So you can see the big difference. So this is a PVT solar air heater. It's a solar air collector. Its length. So that our optimal case, we have a slightly decreased size, and for the thermal. So that's the number of PCM layers we use. You can see in our optimal case, we have a greatly decreased amounts of PCM used in the thermal energy storage. And also for the phase change temperature, we use low phase change temperature. And electrical COP is this one is low because we have a smaller size of PVT system. And so this one shows our analysis initial cost for the different components. So for the PVT solar air collector, they are very similar, but for the fashioned material in our optimal case, we have greatly decreased the size, so the cost is decreased. And for the desiccant wheel and other components are very similar. But that is the operational cost in the different months across a year, and you can see, and our optimal case consumed with the increased operational cost. And so sometimes, so this one is negative because you have a large PVT collector. They will generate more electricity, and when they sell to the grid, you have benefits. So that's why in most cases in the baseline design, they have negative values. And this is for the optimal case. So you can see that from the PVT solar air collectors and the yellow ones from the PCM thermal energy storage system. And this pink ones, they are from the electrical heater. So compared to the baseline cases, so our optimal case is frequently using electrical heater to provide additional heat. So that's why we have a low electrical efficiency or electrical COP coefficient of performance compared to the baseline cases, but we have a decreased investment. And we investigated the variations, the PVT unit price, PCM unit price, and electricity purchase price and sales price on the influence of the design of such system. So clearly, the electricity sale price has a large influence. If you have a large sale price, you have a decreased life cycle cost, but other one have a slightly increased cost. I think that's a very quick introduction of the work we did, but overall is I think a fashioned material could be used as active thermal energy storage. The active, which means we must have additional solutions to control the charging rate and discharging rate, and rather than based on the temperature variation, based on outdoor and indoor temperature variation. So in that case, in many scenarios, PCM cannot really achieve its functional performance. And secondly is the integration of the PCM thermal energy storage with the photovoltaic thermal systems. We'll provide different solutions for heating and cooling, so that in the future we can develop high performance buildings. And lastly, based on our research and observations, so we do need very high cost-effective materials. So these materials, not only from the cost of the material itself, but also for the long-term performance, stability of the performance of material in the longer-term operations. So this is something I think we should work together in the future to overcome this disadvantage, to make these materials and can be a good combination with the solar energy technologies. So that's pretty much. Thank you.
Thank you, Professor Ma, for your elaborative presentation. In fact, it has covered, I think, each and every avenue of PVT when it comes to their application in building energy conservation. So thank you. So I will request the audience, if they have any questions, then they can raise it either through the chat box or even they can ask.
Yeah, Diwakar sir, this is Amrit here from Anna University.
Yes,
Yeah.
please.
Yeah, hi Professor Ma.
Yeah, hello. Yeah.
Yeah. Actually, my question is regarding thermal stability of phase change material. Actually, we used to report like 500 cycle, 1000 cycle, sometimes 2000 cycle. But there is drastic reduction in thermal physical properties if we are doping nanoparticle in paraffin wax as phase change material.
Yeah.
So my question is like, if we are optimizing the loading of nanoparticle, then maybe we could not reach the required value. But if we are going for thermal cycling analysis, there will be a reduction. So what can be a suitable method, like without compromising the thermophysical property, we can enhance the stability of nano enhanced phase change material?
Thank you very much. I think that's a very good question, and also is a very critical question in the use of thermal energy storage. And in the past, so we use both organic materials and inorganic materials. So our observation is, if you use when we're doing the test, we did test in the for the 1 month, and then we didn't use the material at all in the 6 months. So after the 6 months later, when you restart material for the inorganic material, we can see there's clearly a phase separation. And I think they have lots of different technologies, and you just mentioned with the nanomaterials for the optimal loading. And I think the key challenge will be make sure is how we can continuously increase the long-term performance. And that's maybe not only for the nano materials, even for the material itself, that will be very, very critical. And especially, if you said either 500 cycles or 1000 cycles, and even, based on our measurements, after 100 cycles, they will show the very different behaviors. And so this is more critical for the inorganic materials, and because inorganic material is relatively cheaper compared to the organic materials. But I think the possible solution is that really for the researchers working in the material science, they can they can develop some new kind of integrated methods to make sure they generate the stable performance. And from my perspective, so that is one of the I think that this question will have to be reserved. Otherwise, I couldn't say great value for such kind of technology in different applications. For instance, we cannot really replace thermal storage every 6 months. That is very expensive, and PCM material at the moment is also very expensive compared to the other. For instance, in the building construction materials, it's expensive. I hope I answered your question.
Professor Ma, there is a question in the chat box. The question is, how do you see the scope of commercialization of PVT system as the payback period is relatively high? Also, does the geographical location play a critical part in its establishment?
Yes. So I think the work we did for the PVT system and PVT system, I think is a good, is an exciting technology. I think in our case, we looked at the air-based technology. The reason is we want to use the current roof structure to reduce the investment, to make it easy to handle. But for a lot of study also focus on the liquid-based technologies. And I think is really, so this technology, it really depends, the success of this technology, it really depends on, how to use the thermal energy generated from the PVT system. If you cannot really use this thermal energy, I think that it's not much value to use PVT itself. From our test, and this was found that for the electrical efficiency improvement is very limited, and you have to use the thermal energy for the other purpose. Either for the liquid base, you can have the for the domestic hot water or other kind of for the preheating of other systems. So personally, I think the PVT system has more value for commercialization. Actually, the system we developed, that we collaborated with a local company, and they want to commercialize this product, but that is around 5 years ago. And in that time, they didn't really move one step further because they don't think so this product is ready for commercialization. Is really from the long payback period. But I think over the last 5 years with the material price reduction, and so we need to revisit this technology. And personally, I think there is a great value for using photovoltaic thermal systems rather than if you ask me to compare to the thermal energy storage and the photovoltaic thermal system, which one has more value for commercialization? I think that photovoltaic thermal collectors have much more value for commercialization if we can effectively use the thermal energy generated, for instance, in our scenario, or if we can use for the cooling in the summer and heating in the winter, that's provided a lot of value. But for this will make the system is a very, very complicated. So that means optimization and control will be very critical to make sure the success of this technology.
Professor Ma, my question, can I ask, sir?
Sure.
Yeah,
Please.
Professor Ma, thank you for giving an insightful lecture on this topic. So my question is this, that is there any advancement in the identification of cost-effective storage materials from your side?
To be honest, that is not our strong interest, but I do worked with Fraunhofer. I'm not sure you know the Fraunhofer Institute for Solar Energy System in Germany. So they did a lot of research, and I think so. My understanding, so they think the phase change material slurry will be a potential technology, but for the material itself, I cannot comment on specific material. But my thinking is inorganic materials, for the salt hydrate may have more value because it's cheaper and it's cheaper and also have a high thermal conductivity compared to the organic material. Because in many scenarios, we need a faster charging and discharging process. And if you have low thermal conductivity, then you need a lot of other technologies and such as nano and others. That's either on the one hand, you cannot, stability of the material is the one issue. And on the other hand, you also increase the cost.
Yeah, thank you.
Thank you. There is one more question. So one of the participants is asking, other than building application, can we look for some other low temperature application for this PVT?
Yes, of course. That's in the agriculture and for the food manufacturing production processes. First is they have a high value for the PVT system because I interestingly, this year I did some work and collaborated with the industry partner on the work on the look at the this kind of technology, low thermal, but not specifically for the PVT, for heat generation in the agriculture sector, for the drying and for the milk production. I think they have high value because that's, I think, the case will be the liquid based, is not the air based system.
Sure. Thank you, Prasamma. I think if there are no questions, so we can end this session by expressing our gratitude to Professor Ma for this valuable insight. So, thank you once again.
Thank you very much
for your talk and such a productive output which we all got through this interaction. So,
yeah, thank you. If anybody have a question, you can email me and I can try to answer your questions.
Sure. So with this, we can close this session. Thank you.
Thank you.
So now I will request the next speaker. I think he is already there. So Professor Muhammad Hasanuk Zaman. So he is from University of Malaya, Malaysia. So he belongs to Power Energy Dedicated Advanced Center, and today Professor will be giving his talk on challenges in solar thermal energy and thermal energy storage. So welcome Professor Mohammed Hazanuzaman. So over to you for the presentation. Thank you.
Assalamu alaikum and good afternoon. Thank you very much to give opportunity to share some information about the solar thermal energy. This is Dr. Hasanuk Zaman from University of Malaya. Today we shall try to share some information about the challenges in solar thermal energy and thermal energy storage system. Outline of the speech: global challenges, current challenges in energy sector. Before going to solar or thermal energy, we need to know what is the current challenges in the energy sector. Impact on energy and environment, key driver of the energy future. Then solar energy system. Then after that, we shall try to discuss about the solar thermal power plant. Nowadays, very hot topic about the solar thermal power plant. Then challenges of solar thermal energy. What are the challenges? And how we can solve the challenges. Then solar thermal energy technologies, solar thermal energy storage system and application. Then we shall try to discuss the focus on research and development. What type of research we need to do and what type of development we need to do. And last is conclusion and summary. So before starting our main topic, we need to know the challenges, the global challenges. You can see here, out of 10 challenges, you see the top 10 challenges. Top 10 challenges for the next 50 years. So out of 10, you can see number one, and number 4. One is energy, another one is environment. And energy and environment, there is a very good relation. So if there is a good relation, that means we need to focus it simultaneously, both in energy and environment. So nowadays, people are thinking more on energy and environment, how to reduce environmental impact, right? Reduce the emission, that type of things. Okay, so before going to solve our problem, we need to know what type of challenge, how we can overcome the challenges in the field of energy and environment. So we need to know the challenges come from where. What is the source of challenges? Number one is demand side. Demand side challenges. Number two is supply side. Long before, people don't think about the supply side or don't think about the demand side. They just think only one. The energy, we have a lot of energy, just whatever we have, we can consume. But now, all side we need to consider, both the demand side and the supply side. As for example, if we don't think about the supply side, what will be the problem? The problem is we can use more fossil fuel. We don't care the energy source. And another issue is demand side. If we don't consider demand side, maybe we shall use more energy. That will be dangerous for us. Within short time, all the resources will be finished, or lot of fossil fuel need to use. That will be a negative impact on environment. So now the demand side. What is the problem in demand side? Demand side, you can see here. The population, the main concern is our population growth. This is and this is medium case, a different type of forecasting. So if population growth is increased, so the energy consumption will be almost proportional, because nowadays social development, economic development, automation, modernization, everywhere people are using energy. So nowadays without energy, even we cannot think. As for example, our mobile phone, everybody will use mobile, smartphone. So if no energy, we cannot talk, we cannot communicate with each other. Now energy really a big issue. So what is the problem here or challenge here? The current challenge is how to reduce energy consumption. The main concern is reduce energy consumption or increase energy supply to fulfill the demand, because we cannot task this one. We have no option to task economic development or economic growth and social development, whatever you want to say. We cannot task it. We have to supply energy. So what is the option? How we can reduce energy consumption or increase energy supply. So if we go the supply side of the energy, you can see here around 80%, not 1-2%, 80% of energy come from fossil fuel, and 20% is others, traditional biomass, modern renewable energy, or nuclear. Some people say nuclear is non-renewable, or different type of, there is a debate, but we don't go there. So here you can see 80% of energy come from fossil fuel. This is really alarming issue. You can see the 80%, more than 80% of our current energy for heating, cooling, and transportation. Heating, cooling, and transportation. This is one of the clues where we can solve the problem. But how we can solve the problem, that is another issue. So thermal energy, out of 80% of the total energy, you can see the thermal energy is 51%. Huge thermal energy. Transportation 32. We don't think about transportation. Now, if we think only about the thermal energy is 51%, then power sector also we can use, we can consider thermal energy, right? So here, this 80% we can solve. Even though transportation we can use electric vehicle, as for example. If we use electric vehicle, and we can produce electricity from solar thermal, as for example. So that one also we can solve. That means total 80% of energy problem we can solve. So if we think we have a lot of resources, you can see the scenario. This scenario, this is the peak period now is, as for example, now is here. Now I think here, right? This is the peak period. I think this is the peak period. After that, 2050. Then if we go, there are different type of projection forecasting. So this one is sharply drop. Here, as for example, 2100. That means after 70 or 80 years, there will be no fossil fuel. Very limited resources will be there. So how we can run industry? How we can produce our all commodity or all our necessary things? So this is the big challenge. So if we consider about the environmental impact, the climate change. So there are a lot of emissions. I did not go that way. I just want to show you the impact on the climate. So change, right? People are the temperature rising, sea level, ice melting, ocean, and the health problem, agriculture, rain, scheme, ecosystem, everywhere there is a negative impact on the climate change. And this is the one of the cause of carbon dioxide emission from the different sources. So what is the key driver? If we know all, as for example, we know all the issues, all the problems. So what is the key issue or key driver to solve the problem? I think there is no single solution or simple answer. We have to follow the key driver. What is the driver? If we follow, then we can solve the problem. Number one, you can see number one is growth. Demand growth. Demand is growing day by day is growing. Another case, number two, as for example, we can see the supply challenges. What is the supply challenges? Still now 80% energy come from fossil fuel. 80%. Then 80% come from fossil fuel, there is a problem here. Number three, as for example, environmental impact. So if we want to reduce environmental impact, that means there is a supply problem. Then security of supply, number four, as for example. If we reduce this one, as for example, security of supply, not enough energy, load shedding or shortage. The different type of things. So there is an offshore, the technology and policy. What is the technology? As for example, if we consider solar energy, wind energy, hydro, all the renewable energy resources. But problem is The renewable energy resources is still expensive compared to the conventional energy. A conventional power generation system is still expensive. So how we can adapt this one? The adaptation time is important. So there should have policy, different type of policy. What type of policy? Give some incentive, give some subsidy, carbon tax and carbon trading, carbon pricing. So different type of policy we can impose or we can apply for the renewable energy resource-based power generation. So that means these 5 things is very, very important. These 5 key drivers. Number 1 is demand growth. Always we need to think this one. How we can reduce the demand growth. If we cannot reduce, we have to supply the amount of energy. Then if we supply, our system is still 80%. So if we supply, another is environmental impact. If we cannot supply, there will be a problem on security of supply. So we have to have another option that we can consider is technology and policy. This is very, very important. So as for example, people are thinking in these 2 ways. One is energy conservation and management. How much we can save energy in the industry? How much? 10%, 5%, not more than that, I think. How much you can save? And here, simply you cannot save. You need to invest a lot. As for example, high efficient motor, high efficiency equipment. That means you have to replace the old equipment. So there is a also lot of investment. Some are no cost, some are medium cost, some are high cost. So we don't want to go that way. So another option, the best option, whatever we have, we can think the renewable energy resources and technologies. So different type of renewable energy resources. If we implement, there are 1 stone 2 birds. Right? As for example, 2 birds mean you can supply energy at the same time you can reduce carbon dioxide emission or all type of emissions. So this is the good option, but it's still expensive compared to conventional energy. So postpaid, we don't want to go for others resources, just for solar thermal. The postpaid of solar thermal, you can see here, still now PV, still now PV, photovoltaic system. PV is, people are thinking of photovoltaic because this is a small system, 1 kilowatt or 250 watt also can, or 100 watt also can. Standalone system, very small system. Then you can use for your own use. Rooftop, different type of. And if we consider the solar thermal as for example, if we consider water heating, this one is a small system, but we are talking about the big system, power generation, industrial processing, big building application. If we think this one is not small. Right? So solar energy we can use either only electricity, only heat, or both together. Now, this one if we use photovoltaic, we can get electricity. And if we use solar thermal, that means different type of solar collector. Different type of solar collector, we can get heat. So we are working on this one. Nowadays, we are working on photovoltaic thermal. We can get both electricity and heat together. The people are working on it. I think this one is not still now not in the market. There is no commercial product, good product. So we are working on it. So solar thermal, this one is very important in the process heat, industrial process heat. So this one is popular application of solar thermal energy. You can see different type of industries. The industrial process heating system, you can see dairy farm, tinted food, paper, textile, right? Chemical, meat, beverage. So different type of industries we can use. Most of the processes are low grade or low temperature process. We need low grade heat or medium low temperature heat. No need high temperature, medium temperature. Very few. If we want, we can see what is the temperature range here. This figure, this table, you can see the temperature range for this dairy farm. You can see here. Most of the processes is very low, very low. Just dying. This one is. This one is. But most of the processes is below 100 degrees centigrade. That means low temperature heat. That we can easily use solar energy. You can see here very low temperature. Here low temperature, right? Low temperature. Or most of the processes are low temperature. This one is a bit high, plastic, right? But this one you can see mostly is not this one, but mostly is below 100 degrees centigrade. No deep steam, just hot water. And we can use solar thermal system. So if we want to use solar energy system, we can use different type of collector. The solar thermal collector. So what type of collector we need? What is the temperature range? Later on we can discuss. But here we just want to see the different type of collector. This one is non-concentrating collector. This one is concentrating collector. So non-concentrating collector is flat plate collector, right? Then evacuated tube collector. Then concentrating collector. This one is for high temperature. So by using this one, we can 100 degrees centigrade. Good enough for flat plate collector and evacuated tube collector. So this one, this is the time one of the evacuated tube collector. We know the process how. This one is fluid in, the cold fluid, right? Cold fluid in, then hot fluid. And this one, the working fluid. Right? This one is vapor. Then, right? This one solar system, solar irradiation. Then fluid is warm up, right? Going off. Then here, condense, then going down. This in this way, this one is working. Principle of this evacuated tube collector. Then we can collect heat here, right? This one is working fluid. This one working fluid. So we can collect it from the collector. Another one, if we want to use high temperature, for example, high temperature, then we need concentrated system. You can see here, this one is concentrator, right? Parabolic probe. This one is reflector, right? This one is solar radiation, right? This one is receiver, then fluid in and fluid out. We can this. The temperature can, this is depend on how much, 400, 500 degrees centigrade can. So later we can discuss which type of collector, how much temperature we can get from the system. Okay. Then for integration, there are two types of integration. One is supply side, another one is demand side. Supply side. Directly we can integration, a different type of integration. Okay. Then here you can see the solar thermal integration. Hello. Can you hear me?
Yes, sir. Yes, sir. We can hear you.
Oh, I think someone said yes. Oh, okay, okay. So I can continue, right?
Yes, sir. Yes, sir. Please continue.
Oh, okay, okay, okay. I think someone raised hand. Okay. So the simple system thermal integration, as for example, this one is solar thermal collector, right? This one is boiler. But this one in the real system, this is not so simple. It's more complex. There are different type of system, process level, supply level, different type of, right? The integration system. Solar thermal, just to give some ideas. Yeah, this is the collector, this is the boiler. The main is boiler. So boiler can be main source of heat or can be auxiliary. This one can be main and this one can be auxiliary. Right? Or this one can be auxiliary, this one can be main system. This is depend on your system, how you design the system. Right? So hot water is going here. That means the cold water is pumping as per example or working fluid, any type of working fluid or thermofluid, right? Then collect heat. This one is hot water boiler. Then additional energy, if need additional energy. As for example, here the fluid this temperature is 100 degrees centigrade. As for example, but we need steam is 150 degrees centigrade. As for example, so another 50 degrees centigrade supplied by boiler. Yeah, right? They are boiler systems. Right? So this is one of the system. And this process can be supply level or process level. Directly connect to the process. Or this one is supply level. Just this one, right? Or this one can directly connect to the here process level. So there are two types of process mainly. Supply side or supply level and process level. Process level is very complicated because the temperature different other thing need specific temperature, but supply level is very easy. Just additional heat supplied by the boiler. Okay, so solar thermal power plant, if we consider solar thermal power plant, here you can see just one simple example. This is collector. It can be different type of collector. There are so many type of collector, right? Then you can see hot water is coming to the turbine. This one is turbine. The steam, if we consider steam power plant, so steam is coming to the turbine, and this is the generator, right? Then steam again condenser, condense, right? This is the cooling tower. Then condense again, then going back the circulation. This one, right? See here, this one is continuous process, right? The continuous process. And this is the function of boiler, replacement of boiler. What is the function of the boiler in power plant? To produce steam. This is the solar system, just replacement of boiler. The other thing is also same. The condenser, cooling tower, generator, turbine, the steam turbine. Okay. Then challenges in solar. We know this one, the solar energy we can use in industry, industrial process heat or generation or water heating system. Right? So different type of application in different sectors. But what is the challenges of solar thermal energy? The main challenge you can see here, intermittency, issue of solar energy. You can see this figure, right? As for example, this one for AMS, for example. This one is EMS, for example. So you can see the heat is very, very high. And sometimes even there is no sun, cloudy day, foggy. So different type of uncertainty and intermittency. So these are the challenges. So if we want to see bit more details, as for example, N1, you can see you cannot predict it. there are a lot of uncertainty and intermittency. You can see here, this one is here, there, here. Taxation is very, very high, sometimes no sun. So if we consider this one, then seasonal variation, you can see, as for example, for particular area, in a certain area, we can see maybe January is very high. Okay? Then you can see June. Yeah, on an average. Then here, May, June is here. But January, February, March. So if we want to use, so this one will be the problem. We have to design. As for example, if we consider this is our demand, as for example, this is our demand. So there is excess here, excess production. But here is like due to seasonal variation. Okay? This is the main challenges of solar energy or renewable energy or other type of renewable energy resources. Okay, this one. So thermal energy system, if we go, just I want to give a very simple example because I don't know who are the participant. Maybe someone is already expert, someone maybe a student, right here. So the basic, what is the basic component of the solar system? Basic is this one, number one. Number one is collector. And number two is storage tank. This one number one, this one is number two. This is the basic of solar system. The collector, different type of collector. And we can select different type of collector based on the temperature range and application. But this one is very, very important. Everywhere we should have a storage tank. Why storage tank? I already mentioned this one. The intermittency problem, seasonal variation problem, and different type of issues. Yeah. Here, the real solar system, real solar thermal energy system, solar thermal collector. As for example, you can see this one is collector, this one is collector, this one is collector. All are collector. And this one is storage tank. This one is storage tank. We need a storage tank, big storage tank. Why? I already mentioned, sometimes radiation is 0, sometimes is 1000 as per example. Radiation is very high, sometimes 0, sometimes peak, maximum, sometimes is 0. That is why we need a big storage tank. Another issue also, in daytime we have sun, but night time, how we can run industry, how we can supply it. That is also big issue related to solar system. We hydro, the other is not. So challenges for this one, but day night solar energy is our challenge for day and night. Okay, then you can see the big system, very big. So you can, if you go to visit any type of solar, real solar thermal energy system, you will see this one, the collector, different type of collector. This one is storage tank, storage tank, storage tank. And this storage tank is not very simple. How much or how long you can store energy by using this tank? If 2-3 days no sun, how you will supply it? Suddenly very high temperature, how you will manage the additional energy? The design of the solar system is not very Easy. Okay, this one, if we want to see the temperature range of different type of solar system, you can see here 80 degrees centigrade, the standard flat plate water heater. Up to 80 degrees centigrade. Then evaporated tube collector or advanced flat plate collector is 80 to 100 degrees centigrade, 110 degrees centigrade. That means by using this one, we can supply our thermal demand, thermal energy demand by using this one for industrial processing, as for example, water heating, right? Hotel, a commercial and residential building, we can supply our thermal energy demand by using this. So if we need, as per a high temperature for power generation, thermal power generation, right? Thermal power plant, so we need bigger one, parabolic drop, different type of use that one. And as for example, if we need, we can build a cascaded system. One of my PhD students, yes, he has done this one, cascaded system. As for example, we need 100 degrees centigrade water. So up to 60 degree we can use the flat plate collector. Then after that we can use evaporated tube collector. Right? The 60 degrees centigrade to 100 degrees centigrade we can use evaporated tube collector. We can get better efficiency. Then the main challenge here are losses, we can see. The different type of losses of the solar thermal collector. Different type of losses of the solar thermal collector. You can see here the collector area and this one global solar. Right? Then different type of losses. This is called optical loss, right? As for example, this one, deflection, convection, and radiation. These are the losses. Then absorption, right? The net, the light absorbing layer, then fluid. So different type of, and this loss is huge. What is the transmittivity of the glass? Is normal as for example 92%, as for example 92% or 90%. Right? That means 10% loss is automatic there. 10% loss here, automatically 10% loss here. We did this type of experiment in our lab. How we can reduce to different type of. Then after a certain period, maybe 1 year, 2 years, 3 years, or after 4 years, after 10 years, right? The losses will be more. 92%, maybe it will be 80% or 70% as for example. So 30% losses is there. One of the losses, optical loss. Then if we want to see more details, losses, yeah, right? This one is transparent glass. So we know this one is, as for example, here is 90%. That means 10% loss already here. Then here also additional, right? Then we can get different type of losses. Then we can get the thermal energy from the collector, heat from the collector, insulation, and other things, conduction loss, convection loss, heat transfer fluid, right? So different type of losses here. So if we want to summarize all the losses, we can get this type of curve. This one also depends on the average absorbed temperature. That means temperature different. How much? If here, as for example, 20 degree, we can get better efficiency 80% because the optical loss is almost 20%. 20% loss here. Then The rest of 80%, this one depend on, this one is thermal loss, conduction, convection, radiation loss. If the operating temperature difference is very high, right, the operating temperature difference is high, then the convection, radiation, other losses will be. Then you can see is, as for example, for a particular collector, the different collector, different pieces, and for a collector, this one is one of the particular type of collector. So you can see here the efficiency is almost 10% here. If here is 30%. So different collector, different efficiency. So there are losses here. So main concern, how we can reduce this type of losses. So here, if we want to, we know this one different type of losses, different type of system, then challenges. So if the thermal energy storage technology, so if we want to discuss about the technology, the thermal energy storage technology. So technology, right? By technology, there are three. We know already, right? Sensible. We do not want to discuss this one as well. Just these two. Sensible and latent heat. Sensible heat and latent heat. Then by storage material, different type of material is available in the market. As for example, molten salt, right? Phase change material. I think the previous speaker they discussed about the phase change material. I don't want to go into it. Then application, district heat, process heating and cooling, then power generation. So what is the application of that? Right? Then end user, where we can use the energy storage system in industry, residential and commercial sector, or in utilities. So this one we know this one, the sensible heat, this one is latent heat. I think we know already this type of things. So we can store this type of energy, both the sensible heat and the latent heat. Then this one is collector, the solar thermal collector, and this one is thermal energy storage system. That means there is a working fluid, right? The collector is, as for example, is hot, right? Hot fluid. This one hot fluid. This one is cold fluid. That means the circulation. Then this one is thermal energy storage tank, storage system. Then after that, this energy we can transfer heat to what, or heat to power to our energy compression system. The working fluid, right? How? Transfer from. Then thermal energy storage, different type of technologies. You can see number one, here is hot tank. This one is cold storage tank. This one hot storage tank. That means the cold water is going inside the collector, or for different type of technologies like the tower, going to the tower receiver, right? Then it's heated. Then storage in the storage tank. In the storage tank. Then steam is going to the steam turbine or steam generator. Then heat up with more, right? Then going to the turbine. Then this one is condenser. Then this one is pump, just pumping going on. This additional fluid. So different type of arrangement for different. Then this one is generator. So we can generate power. Or here directly steam. You can see here is steam. Steam. Then going to the steam turbine, that condenser, then water pumping, then going to the system, the collector solar system, then is steam, the same thing. So different type of system, different type of design we can use based on our requirement. So thermal energy, you can see the technologies for different type of technology. for energy storage system. You can see these are the thermal energy storage. This one is hydro storage. This is very old technology. Since long before, people are using this one. And when we have excess energy from water, then when we need energy, this water we can use for power generation. Right? So nowadays, this one is almost, you can see, developed. And this one other is developing. Solar energy and lead acid battery. Right? This one is lithium ion battery. So different type of technologies. But solar thermal is also next with technology nowadays we can use for different type of application. Here, if we want to go for energy storage technology or energy storage materials, what type of material we can use? See this one, right? The PCM is one of, I think PCM no need to discuss about this one. You already got all the ideas, all the information. Okay, this one, so different type of PCM. I don't want to discuss this one anymore. So different, so for low temperature, medium temperature, high PCM. Okay, then the application and efficiency, capacity. You can see use not small, 100 megawatt, not a small plant. So pump, is small compared to the big power plant, but in our system, is normal system, is 100 megawatt, 1 gigawatt, right? This one. And the battery is okay, good option, but we can use also compress here. There is different type of system for this one. This one are the current system. Then thermal energy storage and application. If you want to go here, where the key application of thermal storage. So here, variable supply integration. Variable supply. Sometimes in out. When we need, we can use this. Then supply side, right? Then storage, then grid system normally, right? Then right distributed energy resources we can use. Then housing we can use. Then transportation. Transportation is one of the important sector for thermal energy storage as well as cold storage system. One of my students, she did this type of one. If we use the energy storage system, or as for example PCM, what will be the impact? As for example, right? As for example, the wall, if we use PCM or different type of inside a beam or inside the wall, what will be the impact? So there are different type of applications also can. Okay. So the system, different type of system, how we can use demand shifting. Sometimes is demand is very high. So now we can, as for example, night time, low demand, but in the evening, high demand. So demand shifting we can use energy storage system. When low demand, that time we can store energy. It can be heat or any other system we can use, right? Then peak time we can use it. Then variable supply integration, right? Then as for example, sector integration, different sector we can integrate, seasonal we can use. Then network reinforcement we can use. So these are the system where we can use thermal energy storage system. Okay, as for example, if you want to know the key application, where, how long we can use. As for example, you can see the low temperature up to 100 degrees centigrade, low temperature, PCA, then water tank, thermal energy storage system, underground, and thermal energy storage system, Right? So this one you can see sensible heat. Sensible heat we can use until month, hour, day, month. It's long time for every, even the high temperature, sensible heat. But latent heat you can use both thermochemical or mechanical thermal. So you can use based on different application. The voltage or different type of system we can use for different application based on the temperature requirement. Then you can see here the applicable is scale, operating duration, and element. You can see the potential vector where we can use. This one is cooling, heating. This one is cooling, heating, and power generation. Cooling, heating, and power generation. This one is water tank thermal energy storage where we can use everywhere. Small district utility and the storage period, hour, day, week, and month. That means long time we can use this type of heat. Underground thermal energy storage we can use also, right? So everywhere. So these are the latent heat, the sensible heat is everywhere we can use. Latent heat also we can use, right? This one is green color, you can read green color is applicable. And red color not applicable. That means here we cannot use. Right? The short time PCM we can use, but long time we cannot use. But sensible heat everywhere we can use, even though it's small, medium, and big, right? Or short time, long time, and the different potential application. So these are the system, different type of system, and we can use. Then very details, the range of power generation. You can see sensible heat. This one water tank thermal energy storage system. This one is up to 10 megawatt. Right? Then underground thermal energy storage is big, up to 100 megawatt. The temperature range is operating temperature, you can see, and up to 90 degree here, up to 95 degrees centigrade. That means hot water. Then efficiency, you can see, if you want to see, the efficiency is 50 to 90%, efficiency up to 90%. Then duration period, you can see up to month, and week to month, a long time. Then energy density also not very low, 25 to 85 kilowatt per meter cube. This is different type of, and the lifetime is very, very long, 50 years. 50 years. Right? So here is 15 to 40 years, but here is 50 years. So you can see this one, the application. So different type of system. These are the different type of application. Latent heat, kilowatt to gigawatt hour, then megawatt, up to 100 megawatt. Right? Then up to very high temperature, then 90%. So these are the system that we can use on. Then the major application of the thermal energy storage by sector. That means here you can see that here you can see, you can read it. Thermal energy storage technologies are available today for this application. That means thermal energy storage in power sector we can use, right? Then industrial sector we can use. Then heating, cooling we can use. Cold chain, building. So everywhere we can use as a variable supply. Variable supply integration. Then sector coupling we can use. Right? This one we can use. This one. And this one, number 2 is a different color. The technologies are being developed for this application. This is one the important point where we can use hot type applications. Okay. Then if we go for efficiency level and cost, this is one of the important factors. Everybody think. As for example, I want to buy a mobile phone. Which one we shall buy? A normal phone or smartphone? Which one is cost effective? I am not discussing about the costly. If we consider cost effectiveness, smartphone is better than the simple. How? As for example, if you consider all the services and then you get from the smartphone, we no need to buy computer, laptop. And if you buy a simple phone, you cannot make video call. You cannot, right? That type of thing. And you have to buy, if you want to do this type of application, you have to buy laptop or other devices. So if you combine all together, so this one will be cost effective. Even though it's expensive, but sometimes the expensive one is cost effective. So you can see this is depend on, you have to, we need to analyze this one. Which one is cost effective? And even low cost, but not cost effective. So we need to discuss this one. Okay, so you can see the cost. This one. This is not my findings. This one is arena findings. International Renewable Energy Agency. They have done this type of cost benefit analysis. Right? The efficiency. Then now, as for example, 2018 is 90%. So 2030 it will be 92%. Now is 25 to 30 dollar per kilowatt hour. So around 2030, that means after 10 years it will be more or less half, 50%. Okay? Then latent heat also you can see now is 50 to 90. After 10 years it will be 25 to 35. That means 1/3. So different type of technology. This is the that we can use in the power sector. In big size as well. This one is industrial sector, as for example, industrial sector. So now is this. So this one will be reduced, further reduced. And this cost variation is very high because this depends on system, different type of system. Okay? So this one, these are the things. I think time is almost finished, right? Okay, I want to go forward it faster. So these are the cost, different type of technology, and this is the cost. And then you can read better on. This one is long-term plan, short-term plan. This is the findings from the National Renewable Energy Agency. This is their finding. I just sharing information. Okay. Then you can see this one is very, very important. That I discussed. I just make it short. There are a lot of information. Just pick up some information okay, from different sources. There are a range of tools that are available to policymakers seeking to support the thermal energy storage. This one is very, very important. As for example, you have resources. You have a bicycle, but you don't know how to ride it. You cannot use it. We have a lot of resources. The policymaker, if they make it usable, we can use it. Policy and planning is very, very important. So invest in research and development activities and in demonstration project can help to overcome technical challenges. So there are a lot of challenges. I just share some information. There are others, so many challenges. To build the market awareness of the unique capacities of the thermal energy storage system and reduce the perceived risk of deploying them. Then plan. Then you can read here the planning and regulatory framework. This one is very, very important. Planning ensure coherence of energy policy making. For example, as per introduce carbon pricing, I already mentioned the carbon price is one of the important factors. Remove fossil fuel subsidies, the different type of subsidies, as for example, fossil fuel. Many government, many countries, right? The government give subsidies for fossil fuel. So remove subsidies and impose tax on carbon and introduce building code and shift heating system from the fossil fuel. Then implementation of renewable energy based system in building, as for example, building integrated PVT system. And the different types of market structure support the development of technology, neutral market structure to that, so that the thermal energy storage can compete with other sources of flexibility to provide service to the energy system. Hence, research and innovation. This one is very, very important. We need to do research to solve all the issues that I mentioned. Without research and innovation, the decarbonization effect is very, very important. Need effort. So effort means money. Without money, we cannot hire the expert. Or we need research. You need money and this proper place, all the things. The research and innovation is very, very important. So focus on, I think time, okay, 5 more minutes. So focus on research and development. You can see we have no choice, no alternative. You can see here. See, you don't want to discuss very details. The temperature, the base case, right? The temperature. So we have to reduce this amount at least 66%. Huge amount. If this one another 50%. Then if we want to discuss here 94% carbon dioxide reduction from renewable energy resources. This is not simple. We need to do research. How we can use this one. You can see the renewable energy 41%, electrification by renewable energy, this one, energy efficiency is 40%, other 6%. Right? Then summary is this one. The plot scenario, this one is base case, and this one is done. So this one is coming from 42% is from renewable, 42%. Sorry, 45%, not 2%. 45% is from renewable. Energy efficiency is 26%. Then fuel switching and others is 29%. That means main focus is on renewable energy. The transmission, transforming energy scenarios. If we want to do or we want to achieve this type, this target, we need to do a lot of research and innovation. Then, just one slide to explain all the information together. Solar thermal system capital, you can see the different type of technology, different type of collector. This one on glass, right? The investment cost will be low. Investment cost will be low. And installation cost, you can see installation cost, you can say is low. Low operating temperature, we can get up to 100 degrees centigrade. I already mentioned. And the glass plate type, evaporative type, this one, this is dependent. Then if you can see concentrated solar power discs, as for example, the investment will be very high, very high. Then operating temperature high, very high. This is dependent on what type of technology we can use and what is the purpose. Yes, for example, this one, and if we want to use for power generation, the initial investment will be. If, as for example, normal heating, we can use this one. Just 100 degrees centigrade, the low cost. So I think this is the summary. So far, time also limited, right? So there are a lot of challenges, so many challenges in energy sector. Right? The potential solution is energy supply challenge. To innovate and use green energy technologies, right? Make good policy for energy technology. Policy is one of the important factors. I also do research on policy, different type of policies. This one, energy storage technology, different type of energy storage technology. Thank you very much.
Thank you, Professor Mohammad Hasanuk Zaman. So it was quite an illustrative talk covering the peripheries of techno-economics of utilizing different technologies pertaining to solar thermal and other allied areas. And then you touched base upon the storage technology, how it can be helpful to come on the overall cost competitiveness regarding the utilization of this application of the technology. So now I will request the participants if they have a couple of questions, because I think we are running out of time. So maybe one or two questions if we are having from the participants.
Please, sir.
Yeah, please go ahead.
دكتور محمد حسن الزمان. السلام عليكم ورحمة الله وبركاته.
وعليكم السلام ورحمة الله وبركاته.
First of all, thank you for this nice presentation, sir. Actually, you covered a lot of aspects regarding the solar thermal energy systems. And I would like to ask about the storage tank in the thermal system. So what are the materials used in manufacturing for the insulation purpose in the solar thermal energy systems? It's like common things like fiberglass or polystyrene or these things, or there's another thing used in this purpose.
Okay, I don't want to discuss today about the technology side. Okay, I am also not in the side of material engineering. My focus is more on the power generation and mechanical side. You can ask about the technology, not material side.
Okay, sir. Thank you very much.
Hello. Hi, sir. Good evening. Ramesh here.
Okay, good evening, Ramesh, Mr. Professor Ramesh.
Yes, yes. PhD scholar from IIT Roorkee itself. So I have one question. Since you have discussing so many things, and it's very nice to hear you, and it's a great for research as well. So I just wanted to know that right now the work is going on for the storage system. So many work is going on for the storage system. Like combined is the one of the latest trend, but there is a lot of challenges there. So can you please enlighten with the placement of the PCM with the sensible heat storage system? So how we can place that so that we have a higher efficiency in terms of the charging and of course the discharging. So placement I'm talking about, how we can place it. Either we can place in the axial wise or maybe the concentric wise and all that.
Okay, can you make it short again? Short.
Yeah, so I just wanted to know that the placement of the PCM in the sensible, in the combined storage system, how we can place it so that we can have a greater efficiency.
With the permission of chairman, may I come in?
Okay,
Yes,
you can.
Sure, sir. Sure,
I think professor has not just presented anything on this aspect. Anyway.
Yes, sir. I'm just asking because of their experience. I understand.
No. Anyway, okay, please. But he has not covered on this aspect. It's a relevant question, I think. Anyway, Professor, yeah, please continue. Sorry.
Okay.
So are there any other questions other than this?
No, sir. Thank you. Thank you so much.
Okay. Thank you, Mr. Ramesh. So if there are no more questions, so I think, yes, sir.
I have one thing to request. So I would like to thank all the organizer, all the professor for your wonderful presentation. So I may not be continue 2 more presentation to attend with you all because of an emergency work I have to leave. So I would like to thank all the professor and hosts, those who have the professor who have give us a wonderful knowledge to us lah. So I would like to thank each and everyone out here lah.
Thank you. Thank you, Mr. Karma Cheku. So I think if there are no more questions, so
Hello?
we can, yes, any questions?
Dr. Hassan?
Yes, yes, please. Yes,
Yeah,
you
yeah.
can continue. Yeah.
Can you hear me?
I can hear you.
Hello?
Yes, please continue.
Okay, I say if you
Mr.
come
Musa,
to
Mr.
slide,
Musa, yeah,
yeah,
you can
yeah,
continue. You can continue.
please
And
come to slide. If you can come to slide 88, slide number 88.
88.
Yes. Well,
Okay, this one, right?
yes, I can't see. No. 88.
Oh,
Sorry.
it's still.
It's 88.
Okay, this one.
Yeah. This outlook of the, is it a global or which region of the world? The global outlook, is it a globally or there's a region specifically for this outlook?
This one is outlook. This one is global outlook.
It's a global. Okay. Thank you. Thank you.
So if there are there any more questions? Okay. So if there are no more questions, so I would like to thank the speaker, Professor Muhammad Hasanuk from University of Malaya, Malaysia. So it was quite enlightening for all of us to learn and have a lot of takeaways from this particular presentation. So once again, thank you, Professor. So we will be closing this session over here. And then I will be requesting our next speaker, in fact, the organizer of this workshop, Professor R.P. Saini from Department of Hydro and Renewable Energy, IIT Roorkee. So sir will be presenting today his talk on research and development investigations on solar thermal energy utilization and storage at HRED, that means the Department of Hydro and Renewable Energy, IIT in Roorkee. So over to you, sir.
Thank you very much, Professor Divakar, chairman of the session. And I'm also thankful to our organizing committee that at least they have just given the opportunity to me to share the work we are carrying out in the Department of Hydro and Renewable Energy at IIT Roorkee. So basically, because 15 minutes I have to speak, so I will not be going to detail all the R&D, but at least I will try to just cover that what we have actually doing related to solar energy in our center, in our department. So just 2-3 slides, I'm talking about our institute. I think you know that is the oldest technical institution. I can say that in India, or you can say that it was the first technical institution in the whole this British Empire. They started in 1847. So this year we are celebrating 75th years. And since then still we have this administrative building this as a heritage building, and still it's working in the shape. This when it was started, it was the Roorkee College of Civil Engineering, then Thompson College of Civil Engineering, and now then it is the IIT Roorkee. So here we have the 12 departments, separate departments, and 12 branches, different branches under UG program, and some program under dual degree programs, postgraduate programs, more than 50 we have, and the 5 years integrated MTech courses we have 2, and 5 years integrated MSc courses 3, and of course this research program, this PhD available in all the departments. Then straightway, I just speak about the department. Of course, it's a very small department, and basically the name is the Hydro and Renewable Energy. We started working in the hydro, but now that we are covering all the field in renewable energy sources. We have 2 MTech programs. One is basically on hydro and another renewable energy, and one is the environmental management of rivers and lakes. So this MTech program has 30 seats in different these policies, and PhD programs we have only more than 35 students, research scholars. Presently they are working, 50 scholars awarded, and we also have, basically we don't have the UG program in our department, but there are some institute electives in different area. About 6 courses we are running in that. As far as the research area concerned here, as I told you earlier, it was the department on hydro. So this main activities we have in hydropower resources, and but I'm here to talk about what we are doing in solar energy. And in solar energy, we are covering both the aspects like solar thermal energy, utilization, and we are working on the storage also. And of course, because we have interdisciplinary programs, so we have solar photovoltaic power plants also, and all aspects related to PV. So now we can, I want to connect the basics before I just list or present to you that what we are working. So as we all know that the sun is the prime source of all renewable energy. So you know that only 47% of solar energy we are interested in, which can be directly converted into useful form of energy. So that 47%, that means you know that it is reaching to our Earth surface or the receiving surface in the beam radius and diffuse radius. So that we have to we have the concern about that. And again, we know that there are 2 routes to use the solar energy. That is, one is solar thermal conversion. Of course, it is low temperature and high temperature, and other is photovoltaics. And in the beginning, I think yesterday, I think somebody that this solar thermal is the this area is ignored in comparison of the photovoltaic, but it's very important. I don't know that we have to understand the importance of the solar thermal conversion of solar energy also. So now, if you talk about the thermal energy utilization systems, so it's schematic, so that we have the solar energy collection, and you know that because the solar energy is intermittent in nature, that is totally time dependent, that is not in our hand, it is not always available to us. So in order to have the continuity in the energy supply, we must have the thermal energy storage system. And here for PV, we have different kind of storage, that is a PV battery, but in thermal energy we have to have the thermal energy system storage. For this, we have the conference over here. As far as our department concerned, hydro and renewable energy, we basically, I'm telling you that we are not working in the high temperature range, we are working in the low temperature range. And of course, both aspects we are covering, that is the solar energy utilization and the storage also. Of course, there's low temperature applications I'm talking about for heating, cooling, and drying also. So in that case, basically we have 2 areas that exclusively we have done on those areas. That is solar air heaters. You know that is again, there are so many issues related to solar heaters. and another this is storage, thermal storage, and both kind of that is the as the other speakers covered a lot and discussed all the working principles and their various aspects related to packed bed and phase change material. So we have been working in both the type of that. So as this is the solar collectors, so we are not working in the concentrating type solar collector, but of course this flat plate collector we are working that exclusively this solar aerator, which comes under the flat plate solar collector. So I just want to discuss a little bit about that what is the issues related to solar air collectors. So you know that is the heat transfer capability, because in the flat plate collector we have this top cover, which is we know that the transmittivity should be there, then the absorber plate absorptivity should be there, and there that the issue is that the solar energy entrapped in the solar on the solar you can say the absorbing plate, that has to be transported to the load. So in that case, if we have the air so as a heat transfer fluid, so we understand that it's a heat transfer capability is very poor. That is the problem with that. So in that case, we have to have some techniques. Of course, there are various techniques are there to enhance the performance of the solar aerators. That is by enhancement of intensity of solar aerators. It's a booster, we can say that the concentrator, we can say that, but it's a different area. By reduction of the thermal losses, of course, that is there. By improving of heat transfer from absorber plate. That is the core area we are working in. And on this aspect, again, we have by providing packed bed absorbers. Okay, this some work has been done in our this main department, core department, this mechanical engineering department, but we have not this work in this. By increasing the heat transfer, that is again a different area, but by increasing convective heat transfer coefficient using artificial roughness. In this aspect, we have worked a lot, and I think we have the more than 100 research papers for these aspects. So then next, I'll try to discuss that what is this concept of what is the concept of the artificial roughness. So here we can say this is the transparent cover, and this is the absorbing plate, and this is the bottom side of the duct. So we need to allow the heat transfer fluid, that is air. So as I told you that the heat transfer capability of air is poor. So in that there are so many things. Either you can have the turbulator in order to create the turbulent in this, but that is again that will be the cost, that will be on the cost of the pumping power. So we don't want to disturb this main core of the fluid that is in turbulent boundary layer. But we also know that there is a in the vicinity of the surface of the plate, there is a laminar sublayer that can act as the shield between the hot plate to the air. So in that case, that means it obstacles the heat transfer from the hot plate to the fluid air. So what we can do, if we can break this layer by providing because in a conventional solar aerator, this surface is smooth. So if we can create the roughness artificially, that means by some mechanism, so that means we will be able to break this layer, this laminar sublayer. So keeping that in mind, that we just put this artificial roughness. So when this artificial roughness, because the height of the artificial roughness, we cannot extend up so that it will go to the main core of the turbulent. So it just break that. So that means this is the optimized parameter, optimum parameter we have to keep. Otherwise, the pumping power will be increased. So considering this aspect, then we can how we can improve the heat transfer coefficient of this collector, and that is known as the absorbing plate having artificial roughness. So now the question is that what kind of this artificial roughness? So it is found that it will depend upon that, because ultimately we want that to enhance the energy. That means to it is there are 2 points. If you just put this you create the turbulence, of course you can enhance the heat transfer, but simultaneously you have to pay the cost of the pumping power. So in that case we have to select the different kind, or you can say different type, different shape geometries. So keeping that in mind, so many geometries and the shape, sizes of the artificial roughness have been investigated. I cannot say the number is maybe more than 30, 40. So in that case, so for that we need to design or develop a experimental setup. That is, we have developed here. We need a duct where we can change the geometry of the artificial roughness provided with the can say that's absorber plate underneath of this absorber plate. And because these most of the studies we have done in house, in the laboratory, so indoor. So in that we have to simulate the solar radiation system. So then we have just developed the heater, so that the equivalent amount of heat, the solar energy we put by this, you can say by this with the various so you know that the input energy, and then finally there's a blower which suck the air through the duct, and then we measure the flow rate and everything. So that is the basic. This is the cross section of the duct here. So this is then. So as I told you that there are various, and it is available in this, our research papers, the different kind of. So few typical roughness geometries I'm presenting over here, just to have the idea that how we did. So it has the V shape, multi V shape, and there's broken V shape, and there this is the different kind of, there's a this circular ribs we have provided, and then this broken ribs we have provided. So in that, basically what we have to think that we have to enhance the heat transfer coefficient with minimum penalty of the this pumping power. So those are investigated, and then of course we have concluded that some geometry of this roughness are efficient, and some are efficient, but they are very difficult to put on the absorbing plate. So depending upon that, there's so many conclusions. That means so many research papers are available in order to conclude. Another aspect is that okay, time is there. So that means is the jet impingement also there. That means that is new concept. Of course, it is this concept is already there in the heat transfer, or you can say heat exchanger. But we are trying to put this as our one research scholar is working on this, and through CFD analysis and experimental validation, experimental results validations she has done on that, and she is going to submit this in a few days. So these are the this outcome. I'm not going to discuss here. So basically, as I told you, that this area I have to consider, because if you keep on increasing the flow rate, so then the pumping power will be increasing in this area thing, and after that the heat transfer, the energy collection will be the trend is like this. So after some times, that means after some beyond some Reynolds number, that it will be constant, but pumping power increasing. So this point is the threshold point that, but we are interested in this. That means that on this. So accordingly, that the thermal efficiency we have to determine. So that means if you are very much interested to know the thermal efficiency, that we don't consider pumping power, but our interest is to consider the overall efficiency. That means the thermohydraulic efficiency. In that, we have to consider how much power you have spent in the pumping and how much you have gained as a thermal energy. So that will be the effective efficiency call, or sometimes we call this a thermohydraulic. Then these are the some research papers. There, as I told you, so more than 60, 70 papers are there on this aspect. So you can go through that. The next part is, as I told you, we are also working on the energy storage system. In this, you know that it's a basically we work on this sensible storage. And in sensible storage, I'm talking about we started because the very few studies on large size material. And small size material, people, there's so many researches are available in the literature, but on large size material, very few studies. So that we started working in that. That is basically the second. We also work for the latent thermal energy storage. And now that's recently one of my students, he has worked on this the combined sensible latent heat. So that is the this we have worked, and this is the experimental setup we have in our lab. Two different setup we have of this kind of. In this again, I'm telling you that the simulator we have put over here, and this is the charging and discharging. Accordingly, we change the direction of the flow through this. I think that has been discussed by various speakers earlier. So as I told you that because the large size material, this size, shape, and the porosity or the sphericity, that means that depending upon the shape, and this wide fraction. So these are the main parameters we have to investigate, because in this, if different shape you have, so it's not the random filling of material, it is the arranged filling. So we have to arrange accordingly, so that what should be the wide fraction in that. So, and this is the PCM. And let me tell you that this one under one study, we found that the most efficient shape is the spherical. So then that is concluded. That means no other shape will be efficient than the as far as the thermohydraulic efficiency I'm talking about. That we are considering the friction losses as well as the storage capacity and other parameters related to thermal energy. So it is concluded that the spherical shape is the efficient. So accordingly, we consider to put this PCM in this spherical things. The last, as I'm telling you, that one more study we have that's recently this reporter of this session, Dr. Abhishek, he has worked. That means, of course, it is the most efficient shape is the spherical. But if we put some pores in the spares, so what we, so that means it is another study we concluded that it's better that if we put some pore in the things, and the different parameter, the depth of the pore and the diameter of the pore and the location of the pore, number of pores. So based on that, it was optimized that what should be the depth and what should be the this diameter and the number of poles accordingly. So then the combined I'm talking about, it's just we can say that we consider the capsule is a spherical only, and then another this my research scholar he's got the degree in this. That means he just put this combined storage, that means PCM as well as this sensible storage. So this is the sensible storage this packing material, and of the same size we have the capsules of in spherical thing only, and we just put this PCM in this, and then he changed the this ratio, that's 20% PCM, 40% PCM, 60% PCM, and then accordingly he just found that which ratio is more efficient. And then it is found that because there's so many advantage, disadvantages. So here the last slide I'm just putting over here, that if you talk about the charging time, of course the sensible storage charging time is faster in comparison of this this latent heat faster, and this discharging time is again this faster this sensible. But of course, the efficiency, if you are talking about the storage efficiency, is better in the combined sensible storage. So that is the study. now there we can, as Mr. Ramesh asked that, I think this is a very relevant questions over here in advance I'm talking about. It is there, that means the placement, this locations is very important. We found that there's even no studies available that how you will place the PCM in the packing element of the sensible storage. So there's a study is going on that. So that means based on the results will come with that. So these are some papers over here. So I'm talking about that in the conclusion of mine. So what is the suggestions for? I think suggestion is that means that so far as you found that a lot of papers are there on these two aspects, but what I am finding that still we have to work, because these research is still in the thesis or in the papers, but these aspects have not been commercialized, especially I'm talking about in India, so that the researchers, they should work out for the to develop the product based on these research's outcomes. So this is my suggestion, or I can conclude that means there is a need to develop the product, so that immediately based on the research we have done, R&D outcomes, the society can be benefited from that. So thank you very much. I think that's 15 minutes I given. I took 5 minutes more. So it's over to Mr. Chairman. Thank you very much. Hello.
Thank you, sir. So thus session 4 is completed successfully. Now I would like to request the chairman of the session to please conclude the session. I request reporter of the session to please conclude the session.
Now I would like to give the briefing about the session. The workshop 4 of this, the session 4 of this workshop is chaired by Professor
Dr. Abhishek, I think I have another lecture to the another seminar. Can I leave with the permission of the chairman?
Yes, sir, sure. Thank you. Thank you for your
The
valuable
questions, queries
insight.
are there, so they can put in the chat box. So I have to join the other conference. So if
Sure,
you
sir.
permit
Sure.
me. Thank you,
Sure,
Professor
sir.
Divakar. And
Thank you, sir. Thank you.
very much.
So now I want to give the briefing about this session. The session 4 of this workshop is chaired by Professor Dibakar Rakshit from IIT Delhi, and 3 speakers have delivered the talk in this session. The first speaker for this session was Professor Yenjum Ma from University of Wollongong, Australia, and he has delivered a talk on solar photovoltaic thermal systems and phase change material thermal energy storage. In his talk, Professor Ma has discussed about the background of hybrid solar photovoltaic thermal systems. Professor Ma has also discussed about the development of PCM in thermal energy storage and various tests that can be performed to identify its performance under different conditions. In the end, he has shared the knowledge about the integration of PVT and PCM into building energy systems. The second speaker of this session was Professor Muhammad Hasanuk from University of Malaya, Malaysia, and he has delivered a talk on challenges in solar thermal energy and thermal energy storage. In his talk, Professor Hasanuk has discussed about the current challenges in energy sector, impact of energy and environment, and key drivers of energy in future. Professor Hasanuk has also discussed about the challenges of solar thermal energy systems and solar thermal energy storage for different applications. In the end, Professor Hasanuk has talked about the research and development in the field of solar thermal energy storage. The third speaker for this session was Professor R.P. Saini from Department of Hydro and Renewable Energy, IIT Roorkee, and he has delivered a talk on R&D investigation on solar thermal utilization and storage at HRED at IIT Roorkee. In his talk, Professor Saini has shared the details of research work performed in the department. This is all about the session 4, and now we can conclude the session. Thank you so much. Over to you, Professor Debak.
Yeah, thank you. Thank you, Dr. Abhishek Gautam, for summarizing the entire session. In fact, it was a very insightful session when we can see that how different building blocks of renewable energy, we can connect them together and come up with some holistic solution. Maybe it is a bit futuristic at this point of juncture when we are speaking about the levelized cost of energy, and then how it is going to get its space if we are comparing it with photovoltaic. I'm speaking about solar thermal in more specific. So those are some of the key points over which we should ponder. Those are the takeaways when we are attempting to have this type of workshop on energy storage, thermal energy storage more specifically, which will help us to make it a point where we can have some more relaxation on the cost of solar thermal based power generation. So that's what I can conclude with. So I think we can end this session if there are no more pendings, and then we can go to the next one. I think it is the panel discussion which we have, and the recommendations or the takeaways from this entire workshop as the closure. So if not, then we can go for that next one. Thank you.
Thank you, sir. Thank you for chairing the session. And now we will proceed for the panel discussion and recommendation for this workshop. And the chairman for this discussion is Professor K. Murugesan, and the panelists are Professor K. Srinivas Reddy, Professor Divakar Rakshit, Professor Muhammad Hasanuzzaman, Professor R.P. Saini, and Dr. Abhishek Gautam. Let me introduce the chairman of the session, Professor K. Murugesan. Professor K. Murugesan obtained his PhD from IIT Madras, Chennai. He joined Department of Civil Engineering, National Taiwan University for postdoctoral research. Then he joined NIT Surathkal as assistant professor. Presently, he is a professor in mechanical and industrial engineering department at IIT Roorkee. He is a specialist in hydromechanical modeling of concrete exposed to fire, solar-assisted ground source heat pump, mathematical modeling of cooling tower for thermal power plant. He has more than 65 general publications as well as 2 international collaborations. Now I hand over the session to the chairman and panelists to discuss the key points and start the panel discussion.
Professor Murugesan is joining us shortly. We should wait for him for just 1 or 2.
Yes, welcome, sir. Sir, please, I hand over the session to you, sir.
Not able to hear anyone. So am I the one who is not hearing, or everyone is on the same page?
No, sir.
We are
Sir,
not
am I
hearing.
audible?
Okay. Yeah,
Yes, sir.
you are audible.
Yes,
you are
sir.
audible, but I can't hear, sir. That's what I thought. Okay.
Yes, sir.
No worries.
I think, sir, sir is not able to hear us. Professor K. Murugesan, sir, are we audible or not, sir? Hello. Sir, we can't hear you.
Hello.
Yes, sir. Yes, sir. Now you are audible, sir.
Yeah. There was some issue on my headphone. I come to the laptop. Yeah, please.
Yes, sir.
So I welcome to this panel discussion. Shall we ask Abhishek to make the presentation?
Yeah. I request to Mohammed Mustafa, may you please share the presentation because I'm facing some problem with my system. Yeah, Professor Murugesan, you can start now.
Yeah, can you please make it as a slideshow mode? Yes. So in the yesterday and today's technical sessions, we have listened to the speakers and there was a very good interactions between the speakers and the participants. Based on the discussion, these are the important key points we have arrived at. The most important point is the thermochemical energy storage. The research on this area is still in its initial stage. It has got a very good opportunity because it has got very less thermal losses compared to the sensible and latent heat thermal energy storage system. So more focus is required for doing research in this area. And the next point arrived at was eco-friendly and novel composite storage materials with a low cost and high thermal conductivity, which is the need of the hour, which has got high latent heat of fusion and high specific heat capacity of materials are required or need to be developed. So research has to be focused in this direction as well. And another important point is the compact heat storage system based on salt hydrates. That is found to be a very promising technology for solar thermal energy storage systems. And the most important aspect is the selection of salts in such a systems. So this should be based on its operating condition and other design aspects. So and also the toxicity, costs, etc. So the stability of the system also is an important challenge. Mr. Mohammed Mustafa, is it only slide? Yes. The higher cost of encapsulation is one of the key important impediments to the commercialization of PCM-based encapsulated PCM-based systems. Therefore, necessary steps are required to be taken and to develop these novel technologies. And it is difficult for a single PCM to satisfy both heating and cooling demands of buildings, which is a very important application. As the optimal phase transition temperature in summer and winter season are entirely different. So to overcome this drawback, a two-layer PCM can be recommended to increase the performance. Next is the use of PCM-based thermal energy storage system for food drying is emerging as a strong technology to reduce the quantity of food wastage or deterioration. We also heard from some of the speakers in the morning. However, in this direction, in order to focus on this direction, more R&D is required for implementing for the end users. Next, please. So the integration of PCMs with hybrid solar photovoltaic thermal systems might be a promising approach for developing high performance buildings, high energy performance, energy efficient buildings. However, the cost effectiveness of such storage materials and their long-term stability are the two important challenges which need to be researched further. Next point, the heat stored in the PCM during high temperature duration should be discharged. It needs to be discharged in many applications at low temperature duration for consecutive day performance, and in order to utilize this for optimum performance of buildings in which PCM is used as one of the heat storage systems. Of course, more research also is required in this direction. And the next point is most of the CSP integrated thermal energy storage systems are equipped with a 2-tank storage as proposed by, as the research is carried out by one of the speakers in the morning session, which results in increased cost of the system. Therefore, studies are required to develop single tank storage system in CSP plant system and also to study their thermal performance. Next, please. Thermal cycling is one of the important factors which affects the material characteristics. So the material has to undergo thousands of cycles during charging and discharging processes. But there is no proper technology or database available for the thermal cycles of storage materials used in the storage system to determine these thermal cycles. So study also has to be done in this direction. The government should provide necessary incentives on small and large scale solar thermal energy systems to the developers which are working to increase the share of renewable energy in a wide range of applications, especially solar energy applications in our country. For promoting research and development in the solar thermal systems, funding agencies need to provide funds, especially for the researchers to carry out their research work, the development of solar systems that can be implemented in many applications in the society. So thank you. So now the session is open for discussion.
I request to all the panel members to please share your opinion about these recommendations.
Yes. Maybe in order to initiate the discussion, in the morning sessions, I think I've listened to Professor Srinivas Reddy. I think Professor Srinivas Reddy is present also in this panel.
Yes, he is in the meeting, sir.
So, okay, thank you. I was wondering, what about the use of nanofluids in thermal storage systems? Anything, any directions? Because I have seen some nano engineering applications in CSP system in his slides. So what is the scope for nanoscience or nanoparticles or nanofluids on which a lot of research is going on?
Can you hear me now?
Yeah, please.
Okay, thank you. Good evening to all. I think the summary is excellent. You gave a nice summary of all the presentations, and it's very good. And it is a rather comprehensive of various approaches, as well as future direction for some cases. I think the energy storage is very important for improving the reliability, as I mentioned earlier. So therefore, this has a lot of potential for for future research problems, as well as there's a lot of potential to carry out new R&D and even technology demonstration in these areas. Of course, thermal storage has its own distinct advantages at different levels, and cascading these energy storages to different levels is very important. And as you mentioned, the nanotechnology. See, nanotechnology means it includes many material side, not only materials for thermal part, like heat transfer part, or reflect like concentration, like optic side, as well as reflection, refraction side, plus structural side. So nanomaterial can see ultimate objective of these materials is to improve the performance, improve the reliability, and reduce the cost. The cost is important. These are the three main objectives for the energy storage systems. So therefore, nanomaterial in these three aspects, like thermal side, structural side, and optical side, play a major role, because now in India, as I mentioned, the dust is a major problem. So therefore, nanotechnology plays a major role on cleaning of self-cleaning technologies and so on. Plus the structural side, nanomaterial plays nano composites play a major role. But in heat transfer point of view, nanofluids play a role, and not only heat transfer but also energy storage. So a lot of works are going on, or a lot of researchers doing their activities in nanomaterials in energy storage. Not only energy density side, but also the charging, discharging, and round trip efficiency side. So therefore, there's a good potential for this. And another important thing is thermochemical. You have mentioned thermochemical is one important aspect, but going for a seasonal storage, the hydrogen is another important. That's also thermochemical, but in a different format. And so splitting of hydrogen, splitting of water, or methane, or even translating into this other, like other forms, not only thermochemical decomposition, but also electrolysis and other forms or other methods also play an important role. So I think it's a very comprehensive, and there is a good potential for this area to take it forward. And I think the government is also encouraging. Recently, we got a bigger project on energy storage, and to demonstrate low, medium temperature applications in extreme weather conditions like Ladakh. So we are setting up this plant soon, which consists of 3 different energy storage materials. Dr. Divakar is also part of that. So I think this area has a good potential. So with this, I close my remarks on this session. Thank you very much. Hello.
Thank you so much, Professor Reddy, for sharing your thoughts about in the panel discussion. I want to request Professor Divakar Rakshit to please give your opinion about the recommendation shared by Professor Purgi.
Yeah, thank you. Thank you, Dr. Abhishek Gautam, for putting it together, the entire workshop of last 2 days. In fact, I can see that it has touched base upon all the peripheries of energy storage, and more specifically thermal energy storage. So as I was telling that if we want to work on some areas where we want to make thermal energy storage competitive with say batteries, like as we say electrical battery versus thermal battery. So there are a lot of avenues which should be taken care of, then only we can make it competitive in terms of price. So most of the things which you have jotted down in the presentation, that gives the overall picture of it. I think other than that, as sir mentioned, Professor Reddy mentioned, it should be always some initiative from the government side, as well as some startups or industries which should come forward to support this type of initiatives, where the R&D can take some more maturity and come up as a packaged solution. Until and unless we get that type of avenue, it will not be possible for us to make it a competitive technology, what we are having for other like photovoltaic, if I'm speaking about solar thermal. Because if you go to the history, like PV also started at a very different level from what we are seeing it today. So definitely that was the technology which was taken care of. But of course, if with all the specializations or the knowledge sharing which we can have through this type of workshops, through this type of cohort, then I'm sure that someday we will be reaching there, and which will be not very far from where we are today, and it is picking up eventually. So, and one more thing I wanted to highlight over here is that suppose we are speaking about electrical energy storage, or let me just directly go to say the application of lithium ion battery. There also thermal energy technologies can be utilized as one of the helping hand. For example, if I'm speaking about the thermal management of lithium ion battery, they are again phase change material, they are again a thermal energy storage heat dissipating system, can be utilized to make the system more robust. So as long as we can work together to have a synergy, there also it will be a fertile area which will help us to grow in conjunction, or with a lot of mutual interdependence on each other. So with that, I think I will end my views. Thank you.
Thank you, Professor Rakshit. Yeah.
Please, sir, go ahead.
Yeah, please.
Thank you, Professor Rakshit. Now, I would like to request Professor Mohammad Hasanuk to share your thoughts regarding the recommendation which we have shown to you.
Thank you very much again. I think already discussed about the adaptation of PB, and the same also PBT system is very important for government support. As for example, I just give one example, FIT. Many countries, especially Germany, or I can give a Malaysian example. Malaysia started 2011. They started the PB. They give lot of incentive. They bought per kilowatt more than 1 ringgit. They give lot of subsidies and FIT. After that, they try to build up the system. Now, the PV system already matured in Malaysia. Then reduce. Now no more. Now is net metering system. They already removed the FIT system. Now is net metering system. So the same thing for solar thermal energy, I think, same as PV, we need to concentrate on the adaptation, the policy, government policy. Then government gives support at the initial stage, then it will be measured soon. This is the summary from my side. Thank you very much.
I request
Thank you,
Professor
sir.
Murugesh- I request
Yes,
Professor Murugesh to please approve these recommendations.
So thank you very much for your active participation and making the suggestions on the key points which we have developed during the deliberations. Sometimes we may have to think, I feel that, of course, the workshop has been technically very interactive with the participants. I have seen in the chat box a lot of, very interesting, encouraging comments have been received by the organizers. In my personal feeling, in order to, as a concluding remark on this panel discussion, sometimes we have to think whether the solar thermal storage can be thought of as a system, standalone system, or geothermal energy or electrical energy or some other form of energy in combination with the, solar energy, whether such systems will be viable economically and practically possible, if not going into 100%. Sometimes it may be possible also because partly we are using different form of energy and partly we are using the solar energy. So such combinations also can be thought of. So thank you very much. I thank all the panel members for your active participation and making this workshop a very successful workshop and very useful for the participants. Right? Thank you. Thank you, one and all.
Uh, Thank you so much, Professor Murugesan, for your kind words. Well, first of all, I am conveying the apologies from the Professor Seni to all of you for not joining this session due to some other commitment. On behalf of him, I would like to thank Professor Murugesan, Professor Reddy, Professor Rakshit, and Professor Mohammad Hasanuzuman for giving their precious time for this workshop and finalizing the recommendation of the workshop successfully. I'm sure that the session as well as this workshop has provided many benefits to all the parties. Thank you so much once again to the chairman and the panel members of this session. Your participation and support is really valuable to us. Thank you.
Thank you.
Over to you, Siddhartha.
Thank you very much. All the best.
Thank you, Dr. Abhishek, for finalizing the recommendations and concluding the panel discussion. And now I request all the speakers and participants to please turn on your camera for the snapshot for the session. With this, we are closing the event. Thank you to all the speakers and attendees to make this event a great success and showing an overwhelming response to this virtual event. And I wish you all the best for the future and hope we would gain significant knowledge to create awareness about the solar thermal energy storage and eliminate the barrier for the development of new technologies based on solar energy resources. With this, we are closing this workshop, and the The certificates for the speaker and participant will be sent to their mail IDs as soon as possible. And for any query regarding this workshop, certificates, presentations, and contact number of speakers, you can contact on our official mail ID provided on your email or brochure. And if you want to send us the feedback, you can also send your feedback regarding the workshop and suggest the improvement for the workshop, or appreciate us. You want to appreciate us, you can also send us on our official mail ID. With this, we are closing this event. Thank you so much. Have a nice day.
Thank you and bye.
Thank you, sir. Thank you, sir.